Calculating inductors in DC circuits. In this presentation, what we're going to be looking at is time constants. How do we calculate time constants and what do they mean in regards to a RL DC circuit? We're also going to calculate the value of current in an RL DC circuit at different time constants. We're then going to calculate the joules of stored energy that a charged inductor will possess. And then we're going to look at the voltage kick that would be present across the opening of a charged inductive DC circuit. So let's start with time constants and a general discussion of steady state values. In an RL DC circuit, the amount of current that will flow within the circuit will have a maximum value that is determined by the resistance, which is here. The value of current, or the maximum current within this circuit, is referred to as the steady state. And that means once the current has stopped rising and has reached its maximum value. In a DC-RL circuit, the I steady state is equal to the DC voltage divided by the resistance. Now, how long does it take for this current to finally reach its steady state? In an inductive DC circuit, the inductor offering counter EMF will have an effect on how long it takes for the current to gradually rise to its full value. So the time it takes is calculated by use of a time constant. This, a lowercase t, is used to represent a time constant. And a time constant is equal to the induction or inductor henries of the circuit divided by the resistance. Now, what on earth is a time constant? Well, when we deal with RL DC circuits, the current will gradually increase in a steady exponential curve. An exponential curve is one where it starts from zero, has a defined increase over its entire body of a 63.2% of change from one step to the next. It won't ever quite reach the value calculated here, I steady state, but it will be darn close. We're talking 99 point some odd percent. And that's why this particular type of graph is referred to as an exponential. It's also referred to as a logarithmic calculation at times, but that aside, what's important here is that an exponential curve can be divided into 5 equal slots of time. 1, 2, 3, 4, and 5. We can label these as time constant 1, time constant 2, time constant 3, time constant 4, and time constant 5. The total amount of time it takes for the current to reach its steady state value is a value of 1 time constant times 5. So the total amount of time to reach steady state. So we have one calculation to determine what one slot of time is over here. And then we have another calculation to determine what is the total amount of time that it will take for us to reach this full steady state value. Let's take a look at a few examples of this calculation in use. First example we have a 250 millihenry coil and a 10 ohm resistor connected to a 10 volt DC source. That means that we have a source that looks like this, a coil, and a resistor. Now what we want to calculate is the time for one time constant. Well, we know that is L over R, and when we calculate L, we need to convert this back to henries. Moving it 1, 2, 3 decimal places to the left gives me 0.25 henries divided by 10 ohms of resistance. That gives me the amount of time in seconds of 0.025. This would be for one time constant. What if we wanted to know the total time? Total time to reach steady state. Well, we would take this value here and multiply it by 5. So 5 times 0.025 would give me a total time of 0.125 seconds. Total time to reach our steady state. In a DC inductive circuit, all that we're really evaluating is the current. Just the current when it comes to a DC inductive resistive circuit. Now, what value would this steady state value be? ISS, steady state, is equal to E over R, which means 10 volts divided by 10 ohms, rendering 1 amp worth of current. After 0.125 seconds has elapsed, we would see an unchanging current of 1 amp. Up to this 0.125 seconds, the current would be steadily rising in value in that exponential curve until finally it reached almost 1 amp. Let's look at another example. This time we're going to take a 600 millihenry coil and connect it again to a 10 ohm resistor to a 10 volt DC source. The circuit diagram itself should look very similar. It's a series circuit, got an inductor and a resistor. The time of one time constant, we calculate L over R. So that means that for the single time constant, it will take us 0.6 divided by 10 for a time of 0.06 seconds. And that would be for one time constant. How much time would it take total? Well, total time is the same as what we calculated over here, as in 5 times one time constant. So 5 times 0.06 would give me a total amount of time of 0.3 seconds in order to reach what's referred to as steady state. Could we calculate how much time it would take to get to time constant 1, time constant 2, time constant 3, time constant 4, and time constant 5? Yeah, for sure. Well, time constant 1 is simply going to be the first time constant, 0.06 seconds. What about the second time constant? Well, take this and multiply it by 2, 0.12 seconds. What about time constant 3? Well, take one time constant, multiply it by 3, 0.18 seconds, 0.24 seconds, and finally 0.3 seconds. Now, what would be the steady state current value of this circuit? Well, steady state is still a product of the voltage divided by the resistance, which ends up being 10 volts divided by 10 ohms, and the same value of current as in the previous example, 1 amp. So what's different between these two examples then? The steady state current value is identical. What's different is the amount of time it will take for that current to slowly increase until it has reached 1 amp. This one takes 0.125 seconds, whereas this one takes 0.3. Let's take a look at a different calculation. The calculation I want to look at now is one that deals with calculating values on our exponential curve. So here's our exponential curve. And here is the rising value of current, right? This is amps. And this is seconds of time. And we know that we have this divided into 1, 2, 3, 4, 5 equally divided time slots. Well, if we know what the steady state current value is, then we should be able to calculate what the value of current is at each one of these time constant values. And so that brings up 3 different methods of calculating the instantaneous value of current, or circuit value, at each of the time constants. There are 3 different methods to calculate circuit values at each time constant. I'm going to show you each of the 3, and then I'm going to sort of lead you towards the one that I think you probably will want to use because it's easy. Let's face it, easy is king. So let's first look at this one. The first method you could use is your old noodle, memorize. And what you're going to memorize is percentages. So we have time constant 1, time constant 2, time constant 3, time constant 4, and time constant 5. And what we can do is memorize the percentages for each one of these. And what the percentage is the percent of steady state. So at time constant 1, it would be 63.2% of the steady state value of current. So what you could do is take your calculator and take 1 times, because we said it was 1 amp, our steady state current. 1 amp times 0.632 would give me, well, obviously, 0.632 amps worth of current. Time constant 2 would be 86.5% of steady state. It's gradually increasing. Time constant 3 would be 95%. Time constant 4 would be 98.1%. And time constant 5 is 99.4%. And so at this point, you're probably looking at me and saying, Dave, I mean, honestly, that's only 1, 2, 3, 4, 5 percentages. That's pretty easy to memorize. I agree with you. However, when we start looking at capacitors, capacitors are not only going to have a rising value like this, but they're also going to have a decreasing value like that. And these percentages for the 5 time constants will be different. And so for that sake alone, I would say don't simply memorize, because it's going to add anguish to your life, and that's not what I'm here for. So that would be the first method that we could utilize. Second method, it's called a progressive calculation. Time constant 1, time constant 2, time constant 3. It's not strictly just a 63.2% difference. It's a 63.2% difference of the difference. Oh my goodness, that sounds confusing. So what if we wanted to calculate the current at time constant 3? Well, what we would need to take is the current at time constant 2 and add to it the maximum or steady state minus I2 times 0.632. Oh my goodness, this sounds painful in the progress that it would take in order to get down to our answers. It takes forever. Don't do this calculation. This will take you forever. Instead, the easiest method that we have in order to calculate what these different values will be at different time constants is with a exponential curve calculation, also known as a logarithmic calculation. So it's quite simple, and we use it with the Sharp calculator. If you don't have this calculator, then you're SOL, and you will have to work out how to do it on your own or memorize the percentages. For the Sharp calculator, what we're going to be doing is calculating the current at specific time constant, and that could be time constant 1, 2, 3, 4, or 5. And we're going to be calculating that by taking the I steady state bracket 1 minus e to the negative time constant that we would like to calculate. Oh man, that sounds complicated, but I assure you it is not, okay? So first off, we need to know what time constant. So the current value that we're going to calculate at a specific time constant is the number that we are going to enter in here. So what time constant do we want? 1, 2, 3, 4, or 5? So I'm going to put in here 1 to 5. This here, negative, you must enter. And this would be in the calculator found with a button that looks like this. This here is an e, and it's simply got a to the power of, or a exponent function. In order to get this, what we're going to have to do is press the second function button on our calculator, and then the button IN, or in. So if we wanted to calculate for our example of having a steady state current of 1 amp, and we wanted to calculate how much current would be flowing in that circuit at the third time constant, well, it's quite a simple procedure. So let's move it over a little bit here and say, okay, for time constant 3. Time constant 3, let's calculate what that's going to be. It's going to be less than 1 amp, and the steady state value is 1 amp. So we're going to take 1 amp, 1 minus e to the negative third time constant. So what does that look like on your calculator? Well, I know it's not the best image with a calculator on the background here, but you got to bear with me. I know yours won't look physically the same. You've probably got a newer one. It's black and white, but the function should be about the same. So first we're going to take 1 amp. We're going to open the bracket, and we're going to do 1 minus. Now I'm going to enter in second function and then the in button. Second function, in button is right here on my calculator. And then we're going to enter in negative 3. So here's the polarity button, negative, and the digit 3. We have to remember to close the bracket. And then we press the equal sign. And what it tells me is that I reach a value of 0.95 amps. Well, is that going to give me the same current value as memorizing the percentages? Oh yeah, for sure it will. This one is just easier to accomplish every single time. So let's say we use the percent function instead. The percent for the third time constant is 95%. So 1 amp times 0.95, and that's simply using our percent if we want to memorize it, equals, well, 0.95 amps. So this equation that I've shown you here, this is used only for a rising exponential curve, as in a curve that looks like this, rising. There is another slightly different calculation that I'm going to show you when we get to capacitive DC circuits. But I would say by far, this is the easiest method in order to calculate what the current value will be during a rising exponential curve. Okay, let's do an example or two. I've got an inductor. The inductor is going to be a total of 500 millihenries. We're going to have 5 ohms worth of resistance and a 20 volt DC source. So my circuit is going to look like this. Doesn't really matter the polarity at this point. There's my inductor, there's my resistor. Let's calculate a few of the variables or the outcomes of this circuit. First, time constant. What is the time constant of one slot of time going to be for this particular circuit? It's L over R. L over R would be 0.5 divided by 5. When we take our calculator, 0.5 divided by 5, we get 0.1 seconds. What about the total time? Total time is going to be equivalent to 5 times 0.1 seconds, which would be 0.5 seconds. Let's calculate the total steady state. Steady state current will be equivalent to the voltage divided by the resistance. And in this case, 20 volts divided by 5 ohms. 20 divided by 5 will give me 4 amps. So I have 4 amps steady state current. Well, let's work out time constant 1, 2, 3, 4, and 5. We want to know what the time is to reach each one and the value of amps that we would expect to reach at each one of these time constants. So first, let's just deal with the time. We know this is 0.1 seconds. This is 0.5 seconds, and the math is quite easy because 0.1 times 2 is 0.2 seconds. 0.3 seconds. Oh, wait, I can even do this one without a calculator. 0.4. Now, how much current will be flowing? Well, we need to use our logarithmic calculation. It's the easiest method. I is equal to I steady state times 1 minus e to the negative tc. So I'm going to calculate the first one. At time constant 1, I have 4 amps, 1 minus, second function, in button, negative 1, close bracket, equals 2.52 amps. That's a 63% rise from 0. Next one, I've got 4 amps, bracket 1 minus second function, in button, negative 2, close bracket, equals 3.45 amps. Third time constant, 4 bracket 1 minus second function in, negative 3, close bracket, equals 3.8 amps. Fourth time constant, 4 bracket 1 minus second function in, negative 4, close bracket, equals 3.92 amps. And finally, the last one, 4 open bracket 1 minus second function in, negative 5 time constant, close bracket, 3.97. Not quite full steady state, but pretty darn close. And we say that difference is negligible, as in by the 5th time constant, it's pretty much reached that steady state value of current. Let's take a look at how we calculate energy that's stored in a charged inductor. Energy that's stored in a charged inductor will take the form of joules. And so with this equation, joules is represented by the W. 0.5 is a constant numeric value we will use with the calculation. L is measured in henries. And the current is the current at steady state. Steady state value of current, or really it could be the current at any time, but I'm going to use the steady state current value. So if we wanted to know what amount of energy was stored in our last example at steady state, remember our last example had us calculating a value from 500 millihenries and a 5 ohm resistor, 20 volt DC source. We had a steady state current of 4 amps. And so what that means is that we could take this information and enter it into our calculator. 0.5 times 500 millihenry is 0.5 again, times the current squared, 4 squared. Once that inductor has reached its full steady state value, how much energy in joules will it be storing? Well, 0.5 times 0.5 times 4 squared gives me a value of 4 joules. So it's a pretty simple calculation, and typically it's used to determine the amount of energy in a fully charged inductor, and so that means we're calculating it once we've reached the steady state value. All right, so let's look at the final calculation to do with DC circuits with a inductive resistive component, and that's this here, inductive voltage kick. Inductive voltage kick takes into account the voltage that is going to be generated when we open the circuit. So we'd say that's the voltage kick. L being the henries of our inductor. Change of time. And so this is the time taken for current to change. And usually it's an extremely small amount of time. And then finally, the last one up here, this one is current, but this is the change of current. And so the easiest way for us to calculate that is original amps minus the new amps. It's a pretty simple calculation. So let me just sort of lay it out for you with a few examples. All right, so let's look at an example where we have a DC circuit and we have a 1,000 millihenry coil, and it's going to be connected to a resistor of 5 ohms, or sorry, yep, 5 ohms, and we're going to have a voltage source of 25 volts DC. The steady state current value of this is going to be 25 divided by 5, giving me 5 amps. Now, what we're going to do with this circuit is we're going to introduce a switch. So there's my coil, there's my resistor, and currently it's all charged up, 5 amps worth of current flowing through the circuit. I'm going to open the switch. When I open the switch, there's 2 different things I need to be aware of. First, how long is it going to take for the current to drop? So the time for the current to drop to 0. Well, for most of us, that's going to be an infinitesimally tiny amount of time. And so what I'm going to measure it in is 4 microseconds, which is absolutely tiny. And 4 microseconds, if we wanted to write that, is going to be 0.12345 6 decimal places, seconds. So that's the amount of time it takes for the current to drop to 0. Now, the other thing that we need to be aware of is what amount of current, what is the current going to be? What is it starting at, and what is it dropping to? So the current change for this particular scenario, because it's a switch, and we know it's going to break the circuit entirely, the current change is from an original current of 5 amps to 0 amps. So that means the total change of current that we're going to have is 5 full amps. 5 full amps. So let's plop that into our calculator and see what we get as a value. So remember, E is equal to negative L, the change in current, over the time it takes to change that current. So we've got 1,000 millihenries. 1,000 millihenries is 1, so we put negative 1. And now we're going to calculate my current change, which is 5, over the amount of time it took for us to reach that, 0.1234. This was my 4 milliseconds. Whoops, what did I put in here? 6? It should be 4. There we go. That makes a lot more sense. Let's work with numbers that make sense. So finally, when I enter that into my calculator, I'm going to put in 1 negative bracket 5 divided by 0. 1, 2, 3, 4, 5 zeros, and then a 4, close bracket, equals. And what we end up with is a massive number, 1 million, or 12 million rather, 12,500,000 volts. So I've got, actually it's 1.2 million volts. So over a million volts. Crazy voltage. That's a lot of volts. So all we've done is we've taken the change of current and divided it by how much time it took for us to change that current. Let's look at one more calculation with this. Let's say we've got a 500 millihenry coil, a 2 ohm resistor, and a 9 volt DC source. What we're going to do with this is calculate what the inductive kick would be when I open the switch. So here's our source, there's our switch, inductor, resistor. Let's work out the I steady state. I steady state is going to be E over R, so 9 divided by 2 is 4.5 amps. When we open the switch, the time it takes for me to open it is going to be extremely short because I can flick the switch almost instantly. So time, the time that I'm going to use, and I'm just choosing this is not a set amount of time that you have to memorize or anything like that. I'm giving it to us. The amount of time that I am going to have in order to open this switch is 2 microseconds. 2 microseconds is representing 6 decimal places. So that means that I have 0.1, 2, 3, 4, 5, 6 decimal places. So 0.000002 seconds. The amps, what is the amps changing from and going to? Well, it's starting at 4.5 and it's going to 0 amps. That means a total change of 4.5 amps. So let's put it into our calculation. E is equal to negative L, bracket, current divided by time. Total amount of inductance is negative 0.5, bracket. Total amount of current change, 4.5, divided by time, 0.1, 2, 3, 4, 5, and then the number 2. Crazy small number. We enter it all into our calculator. So I got to enter in my negative 0.5, bracket, 4.5 divided by 0.1, 2, 3, 4, 5 zeros, and then a 2, close bracket, equals 1.125. million volts. That's quite a voltage. Off a 9 volt DC source. If you come into face-to-face training, we'll do a demonstration of this. I'll poke you with a 9 volt battery and an inductor. And although we won't get 1.1 million volts, still enough to make people squirm, which I find to be quite funny. That's all for our calculations of inductive resistive DC circuits.